the work is nothing but equal to PdV work. When a system changes from state 1 to the state 2, or you can also write this one as a W1 to 2, that is nothing but 1 to 2 PdV. PdV, right? So the constant pressure process, this is the constant pressure process where N is equal to 0. That means here P1 is nothing but equal to P2. P1 is nothing but equal to P2. This is the expansion process. So in expansion process, volume changes from V1 to V2, right? So this is here. Now finally what you can do, that is the PdV, P into V2 minus V1. So this is nothing but equal to W1 to 2. When you apply this one here, Q is equal to delta U. That delta U is nothing but equal to MCV T2 minus T1 plus this is the system changes from state 1 to the state 2, W1 to 2. This W1 to 2 is nothing but this is the relation. W1 to 2, here you need to apply. Then we know that according to the first, that is Cp minus Cv, difference in heat capacities at constant pressure and at constant volume, that is nothing but equal to R. Whereas this Cv is nothing but equal to R by gamma minus 1. Cp is nothing but equal to gamma R by gamma minus 1. What is this here? That Cv is nothing but equal to R by gamma minus 1. So you need to substitute that Cv is equal to R by gamma minus 1. R by gamma minus 1, right? So when you, that is here, when you get this particular relation, that is we know that PV is equal to MRT. When a system changes from state 1 to the state 2, that is P1 V1 is nothing but equal to MRT1. MRT1. The same way, P2 V2 is nothing but equal to MRT2. So when you apply these basics into this particular equation, so finally you are going to get the expression like this one. That is Q1 to 2 is nothing but equal to MRT2 minus T1 into, that is 1 by gamma minus 1 plus 1. So this is the heat transfer relation for a isobaric process. This is the work transfer relation for a isobaric process. Work transfer relation for a isobaric process, right? So that is the developing the heat transfer and work transfer relation. Hope this particular concept is clear. So this is how you have to write the, or you have to develop the expression for heat work transfer and heat transfer relations when a system is undergoing the isobaric process. Undergoing the isobaric process. The examples are also mentioned here. So try to observe the examples. This is constant pressure process or isobaric process. Next one is the constant volume process or isochoric process. Constant volume process or isochoric process. So here, this is nothing but the gas is getting expanded from initial state 1 to the final state 2. Gas gets expanded. Sorry, the gas is getting compressed. So when a gas is getting compressed, the pressure is going to increase. Gas gets compressed, the pressure is going to increase P1 to the P2, right? This is the compression. When the gas gets expanded, when the gas gets expanded, the pressure, so this is the P1, this is the P2, and this is the expansion. The direction is also very much important. So now you have to write. So that is in this isochoric process, PV to the power of n is equal to constant. That means here n is nothing but equal to infinity. N is nothing but equal to infinity. So when you apply the first law of thermodynamics, Q is equal to delta U plus W. So when a system changes from state 1 to the state 2, so this is also W 1 to 2. Or in another way, you can also write this one as Q1 to 2 is equal to, this is the U2 minus U1. This is the point function and the path function to be written as like this one. So this is the path function. This is also the path function. Means the heat transfer and work transfer are occurring at the boundary phenomena. It depends on the path of the system. Whereas this internal energy is nothing but a point function. It depends only on the initial states and final states of the system. So the work done, that is W1 to 2 is nothing but equal to integral of PdV work. So that when since volume remains constant, V1 is equal to V2. So in that case, W is nothing but equal to 0. So in case of a constant volume process, work done is equal to 0. So when you apply the first law of thermodynamics, Q is equal to delta U plus W. So this W is going to become 0. That means Q is going to become delta U. That delta U is nothing but equal to MCV T2 minus T1. MCV T2 minus T1. So this is the heat transfer relation. This is the heat transfer relation, and this is the work transfer in a closed container, in a closed process, right? So this is all about the constant volume process. That is, you can call it as the isochoric process. So what are the heat transfer and work transfer relations to be built up? The examples, try to go through the examples here. The examples, a gas in a closed rigid container. This is the gas in a closed rigid container. Heating the gas will raise its pressure. Heating the gas will raise its pressure without changing in its volume. However, the quantity of gas remains constant. So the effect of heat addition in a constant volume process is to increase the temperature and consequently the internal energy of the system. See here, this one, right? So the effect of heat addition in a constant volume process is to increase the temperature and consequently the internal energy of the system. So this uh, where a student has to remember in this particular case. Next one is the isothermal process. Next one is isothermal process. So in a isothermal process, the equation, that is PV to the power of n is equal to constant. In this one, n is nothing but equal to 1. It is the isothermal process. So apply the first law of thermodynamics. Q is equal to delta U plus W. When a system changes from state 1 to the state 2, that is, this is U2 minus U1 plus W1 to 2. So this W1 to 2 is equal to integral of 1 to 2 PdV, right? And we know that PV is equal to constant. PV is equal to constant. So in that one, when a system changes from state 1, P1, V1 is equal to constant. That is equal to system changes from state 2, P2, V2 is equal to constant. So in this case, what is P? P is nothing but C by V. Then substituting here, W1 to 2 is equal to integral of 1 to 2. What is this pressure? What is this pressure? That pressure is nothing but this one. So C, bringing the volume terms to this side. So C dV by V, right? So constant at the outside, integral of 1 to 2 dV by V. So that what you can write, that dV by V is nothing but equal to C, right? Natural log, that is the ln V 1 to 2. So this is how you are going to write that one. W is equal to this C is nothing but P1 V1 ln V2 by V1, right? So when you apply the limits, then W is equal to P1 V1 ln V2 by V1. And this is this P1 V1 is nothing but you can also write it as a MR T1 ln V2 by V1, right? So W is equal to this constant is nothing but here P1 V1 ln V2 by V1. Then this P1 V1 is nothing but equal to MR T1 ln V2 by V1. So in terms of the pressure, that is you can also write it as MRT1 ln. So the volume and the pressure are inversely proportional. Now here you will get it as a P1 by P2. Here you will get it as a P1 by P2, or that is nothing but equal to P1 V1 ln P1 by P2. See here P1 by P2, and here V1 V1 P1 V1 ln V2 by V1. This is how you have to observe the expressions into this particular isothermal process. So in an isothermal process, again, because Q is equal to delta U plus W, that delta U is nothing but equal to MCV T2 minus T1, MCV T2 minus T1. And in the isothermal process, temperature remains constant, that is the T1 is equal to T2, T1 is equal to T2. So in that case, Q is equal to delta U plus W, and this is going to become 0. Why? T1 is equal to T2, MCV, see here, right? So this U2 minus U1 is equal to 0. That means the expression what you are going to get is Q is equal to W, that is nothing but equal to P1 V1 ln V2 by V1 ln V2 by V1, and this is nothing but equal to MRT1 ln V2 by V1. And in another words, or in another form, where you can represent in terms of the pressure, when the volume data is given, then you can use this formula. But sometimes you will get the pressure data. So P1 V1 ln volume is inversely proportional to the pressure. Now here you will get it as P1 by P2. P1 by P2, right? So that is this is MRT1 ln MRT1 ln P1 by P2. MRT1 ln P1 by P2, right? So that is both the heat transfer and work transfer. That is Q is equal to W is equal to this one. So this is the relation you are going to get in isothermal process. Hope this is these things are clear in developing the expression for the heat transfer and work transfer for a closed system at isothermal process. In isothermal process, right? Now, this is you can also call it as a hyperbolic process or a quasi-static process. Hyperbolic process or quasi-static process. In both the cases, PV is equal to constant. So hyperbolic process is the one in which the product of pressure and volume remains constant during the process. Even in the quasi-static process also, PV is equal to constant. So the quasi-static process is nothing but a process which occurs in an infinitely slowly. So that is nothing but the quadratic. In that case, PV is equal to constant. So the curve for such an expansion process is a rectangular hyperbola, and hence this is known as hyperbolic expansion, and hence this is known as hyperbolic expansion, right? The examples you can consider over here as constant pressure or isothermal process. Example is you can the melting of ice at 0 degree, melting of ice at 0 degree. So the in the especially for the phase change process, when a phase change, that means conversion of a solid state to the liquid state, it is nothing but the phase change. In that particular cases, the process which is going to occur at constant temperature and constant pressure. So the constant temperature, that is melting of ice at 0 degree, that means conversion of a solid state to the liquid state at 0 degree. So that is nothing but melting of ice. Even the evaporation of a water, that means the conversion of a water at 100 degrees centigrade into steam or gas at 100 degrees centigrade. So there 100 degrees centigrade, the evaporation process is going to occur. So that is also nothing but the isothermal process. So changes in the state or phase changes of different liquids through the process of melting and evaporation are the examples of isothermal process. So one of the examples of industrial application of the isothermal process is the Carnot engine. In the Carnot engine, there are two processes are there, that two processes which occurs in isothermal condition. So refrigerator also works in isothermal condition. Refrigerator also works in isothermal condition. Why? In the evaporator, the temperature remains constant, right? In the evaporator, the temperature remains, sometimes the temperature is going to be -4 degrees centigrade, or the temperature may be -10 degrees centigrade. So like that one, there are things. Next, the heat pump is also comes under to the isothermal process. Heat pump, right? Where you need to maintain the room temperature constant around 30 degrees centigrade or 35 degrees centigrade, especially when the outside environment is very low, right? So outside environment is sometimes if the outside environment is 4 degrees centigrade, body cannot accept that particular 4 degrees centigrade all the time. So you need to maintain the room temperature as 30 degrees centigrade. So that particular task is taken up by this heat pump. Whereas the refrigerator is nothing but which maintains a low temperature compared to the environmental conditions, right? So that is what the refrigerator and heat pump. These are the examples you can take up to this side. Next one is the adiabatic process. So a process in which there is no heat interactions taking place between the system and the surroundings. No heat interaction between the system and the surroundings. So that is Q is equal to 0. So here Q is equal to 0. No heat interactions. Neither the heat is entering nor the heat is leaving from the system. So that is heat transfer is 0. In this process, only the work interaction is at the expense of internal energy. Why? It is a stationary system. Q is equal to delta U plus W. When you write it is the adiabatic process, this is Q is equal to 0. That means it is going to occur, the adiabatic process which is going to occur at the expense of internal energy, Then how you are going to write this particular derivation, that is, this is nothing but the work transfer for a closed system in adiabatic process. So what is that? How you are going to arrive that one? When a system changes from state 1 to the 2, that is the W is equal to PdV, integral 1 to 2. This is nothing but PdV. But we know that P1 V1 is equal to P2. See here, P1 to the power of gamma, because it is a adiabatic process. So to the power of a polytropic PV to the power of n. It is a polytropic process, one process. So for a reversible adiabatic process, that is gamma is equal to constant, right? So this is the reversible adiabatic process. Reversible adiabatic process, you can call it as a isentropic process. You can call it as reversible adiabatic process. You can call it as isentropic process. So that is PV to the power of gamma is equal constant. So on that case here, P1 V1 to the power of gamma is equal to P2 V2 to the power of gamma, that is nothing but equal to constant, and this is nothing but equal to PV to the power of gamma. So what is here the pressure? So that pressure P is equal to C by V to the power of gamma. Substitute over here. Integral 1 to 2 constant, bringing all the volume terms dV by V to the power of gamma. V to the power of gamma. Right? So the integral of x to the power of n formula, that is x to the power of n plus 1 by n plus 1. Strong mathematics is also applied, that is either the differentiation or the integration you have to apply here. So onto this particular point where it is written as integral of 1 to 2 constant take out. So this is v to the power of minus gamma dv. Now you differentiate this one. So you will get as this C, and this is v to the power of minus gamma plus 1 divided by 2. Divide by minus gamma plus 1. The limits are 1 to 2. So what you will get here? C into v2 to the power of minus gamma plus 1 minus v1 to the power of minus gamma plus 1 divided by minus gamma plus 1. Minus gamma plus 1. But what about this C? See, here there is a volume V2 is there. So I will write that volume that is as in this way, that is P2 V2 and V2 to the power of minus gamma plus 1 minus, again here it is the P1 V1 and V1 to the power of minus gamma plus 1 divided by minus gamma plus 1. So this is cancelling, that is right, minus sorry, this is also here gamma, this is also gamma because it is this one p1 v1 to the power of gamma. So this is getting cancelling and this is also getting cancelling. So finally you could able to get p2 v2 minus p1 v1 divided by minus gamma plus 1, right? When you arrange the terms, you will get it as p1 v1 minus p2 v2 by gamma minus 1, right? So here it is the P2 V2 minus. So when we solve this particular expression, so when you solve this particular expression, finally you will get the work transfer relation as P1 V1 minus P2 V2 by gamma minus 1. So that is here you will get as a P2 V2 minus P1 V1 by minus gamma plus 1. Then you can write this one as P1 V1 minus